All right, let me just hit these announcements fairly quickly. If any of you are anywhere close to graduation, think about applying. If you're graduating in the fall, or if you know of anyone who is, they've got to have that graduation application in right now, I mean, as soon as possible. And I don't know if y'all know, we have gone to fall term graduation exercises. It used to be we only had one a year, and that was in the spring. So many graduates were getting to do it anywhere on campus, so we had to do it at the Civic Center, and that was a big cost, and it was sort of a big hassle, and just so many people. Now we're going to do fall and spring, and that way it'll be manageable. We can do it on campus. It can be a lot more interaction with all the graduates, you know, rather than having so many you can't possibly interact with them all. So we've gone to that, so that's why we've got to get it. If you're graduating this fall, this is the first fall we've done that. And the process is a degree audit, which is what you were just doing, seeing your advisor, which we were just doing, and you will later, and then you apply online. The better thing, rather than waiting until the term that you're graduating, apply the term before you're scheduled to graduate, just like Clark was trying to do, figure out what to take next term so he can make progress toward that. If it's a term before you're going to graduate, do the audit, do all this now so you'll know what you have to take in order to complete the degree. And then when the schedule comes out, if you don't see one of those courses on there, then we can contact somebody, you can contact someone and say, hey, can this be offered this spring because I need it to graduate, and maybe they can add it to the schedule. Or if not, we can do a course substitution and figure that out. But if you have that extra term there, it gives you a lot of flexibility. When it's the term you're graduating, you're stuck with what you're taking, and then you're either going to graduate or not. So more flexibility. Two other things, they're looking for note takers. Office of Student Services, they will pay you to take notes, usually for a student who has some sort of disability that can't take notes for himself or herself. And also they're looking for peer tutors in the Space Center. And right now they list math, English, biology, computer science, and Spanish. I saw a lot of you probably have computer science. I know you have enough math to be tutoring anyone that needs it. Okay, so please consider either one of those. All right, now, why is it this slide that's popping up here? Oh, because example 11 didn't have a slide. Okay, so what are we going to do here? It says find an average value. F of x is equal to 10x. Let me get my pen set up. F of x. Any questions before we get started? I'm sorry, I just launched into it. Any questions? Okay. F of x is equal to tangent x. Okay, and we're to find the average value of that on the interval 0 to pi fourths. All right. Now, number one, does this problem make sense? Where is tangent defined?
From 0 to pi halves.
From negative pi halves to pi halves. Tangent is defined. Those are your vertical asymptotes, not defined on those vertical asymptotes. So anything between negative pi halves and pi halves, yes, and that certainly fits within that. So we can do the problem. Okay? Now, it's asking for find the average value, okay? Now, I don't know if you remember how to do average value. It's been a while. Do you remember? Don't know if this will shake a few cobwebs loose or not. If this is your tangent function, something like that, right? And you're going from 0 to pi fourths. Okay, in there. So you're just doing this average there. I mean, you're finding the average value between those two places. Okay, see, this is pi halves, this is minus pi halves. Pi fourths would be about halfway in between that. Okay, so that's the area under the curve. Okay. And the average value would be what straight line there would give you that same area. Okay? See, this area would be included, that would be, so you add this and take off that, and they need to be about the same. So that would give you your average value. What horizontal line would do that? Okay? So you're looking for, and that's going to be your Y value. Okay? Now, and here's this. What's that? Oh, yeah. Really?
Like, I drove through like 3 separate rainstorms.
Wow.
Yeah. And I stay like at home, but that's not even
Yeah. Yeah, I live in Forest Park, which is outside Birmingham, and it's, I know exactly how you get it from there, or maybe not the exact route, but yeah, about how far you go. Okay. So that's what we're looking for. What is that Y value that has the same area as the portion under the curve? That's what we're looking for. Well, the same area as portion under the curve, that would be the integral from 0 to pi fourths tangent x dx, right? That's going to be the area under the curve, okay? Now, that should be equal to this Y value. Let's see if they have a name. Let's call it AV for average value. That's some Y value multiplied by, that's your height, multiplied by the width. And the width is simply pi fourths minus 0, right? So this average value that you're looking for is equal to 1 over pi fourths times the integral of 0 to pi fourths tangent x dx. All this is doing is giving you an example of when you might need to integrate a tangent. And you remember how to integrate a tangent. That's what we spent a lot of last time figuring out, not just tangent, but all at once. And you know, I do know this one, but if I didn't, I'd just go look it up. Because it's in every trig table integration table you have. But you can just look up at the top of the page, and what you see the integral of tangent u being.
Negative log, absolute value.
Cosine. Yeah. And you know what? Because that's the same as log of absolute value of secant. Because you could do the minus 1, put that as the exponent for cosine, and 1 over cosine is secant. So I like that one just as well. Well, no, cosine might be easier, so let's leave it like that. So this will be 1 over pi fourths, and this integral will be minus the log of absolute value cosine of pi fourths plus, okay, wait, I'm sorry. I'm skipping too many steps here. Okay. Evaluated from 0 to pi fourths. Okay. Wait, let me back off. Okay. I was skipping a step there. I probably shouldn't have. X. Okay. When you do the antiderivative of tangent, you get minus log of cosine after the value of cosine x. Okay? Now, time out here. Cosine x between 0 and pi fourths is always what? Positive. Everything in the first quadrant is positive. So you can lose the absolute value loss because cosine is positive from 0 to pi fourths. Okay? So, what we can do now is, don't forget your 1 over pi fourths. In fact, I get a little tired of writing 1 over pi fourths. That's the same as 4 over pi. Are you okay with that? 1 over fraction is the reciprocal of that, okay? So that would be that times minus log cosine of pi fourths minus a minus, which is plus the log of cosine 0. Do you buy that? Yay or nay? To do a definite integral, you plug in the top one minus plugging in the bottom. Well, you had a minus here to begin with, so when you do a minus of a minus, that makes it positive. Right? You're doing this entity first evaluated there, minus evaluated there. Well, this entity is negative, so when you subtract the minus, that makes it a plus there. Does everybody see that? Whatever your dx is, the x is what these are plugging in for. Okay? Now, does anyone recall what, all right, I'm going to take off my drawing here if that's okay, because it's sort of messing up my, maybe I shouldn't have, but I did anyway. Too late now to turn back now. Okay. That would be 4 over pi times the minus the log of, does anyone know what cosine of pi fourths is? Root 2 over 2. Okay. Root 2 over 2 plus the log of, what's cosine of 0? 1. Okay. Now, this will be 4 over pi times minus the log of the square root of 2 plus the log of 2. Okay? The log of a quotient is the difference in the logs. That's one of the log rules. Y'all remember that? Probably not.
How is that the difference?
What's that?
I just don't understand how that's the difference.
Okay. Well, there's a minus in front. Okay. If you didn't have this, it would be this minus that. But with a minus in front, that makes this minus and that plus. Right. Sort of like we did before. Now, anyone remember what log of 1 is?
Negative? No, is it
0.
0?
So we're through with that one. Okay. So basically, it's log 2 minus log of root 2 times 4 over pi. Now, that's one way to write the answer. There's a little bit easier way if you remember that. Remember you said root 2 over 2? Where did we get that? That's the same as 1 over root 2. So basically, you could have just done, this will be, and you can go back and do the math if you want to, 4 over pi times the log of root 2. Now, no, minus the log of root, no? Let me think a minute. That would have been a 1. Yeah, times the log of root 2. Okay. Which, there's another log thing if you could do it if you want to. 4 over pi times 1/2 the log of 2. Okay. Because this is log of 2 to the 1/2, bring the 1/2 in front, and it'd be 1/2 log of 2. So that would then be 2 over pi log 2. Okay.
Yeah, I do remember that now because
What's that?
isn't you just do like the step down, like a quotient is subtraction and
Right,
multiplication
exactly.
is adding.
Right, right. Yeah. Did you hear that from me? Okay, I thought you did that. I've never heard anyone else think of it that way, so I thought, boy, you've been around somebody weird. Okay, never mind. Okay, yeah. Now, check your book. Get on your calculator. 2 divided by pi times log 2 and see what you get. They say you're supposed to get 0.441, and I've made so many sign changes here, I want to make sure that I haven't done something stupid. 2 divided by pi times the log of 2. To me, that's a much simpler answer than the one they give. But
Yep, that's what I got.
0.441? Yeah, okay. I thought it was the same. Okay. That finishes 5.2. Homework exercises here would be any questions on this before I leave it? Again, this is sort of a bizarre sort of problem. Nothing outstanding about it. It just sort of reminds you how to do an average value and has some weird numbers, but it works out. So homework exercises, any of the odds 5 through 27. They're all at Calc Chat, 9's at Calc View. Either 29 or 31 or both. They're both at Calc Chat, 29's at Calc View. Any of the odds 33 to 41, they're all at Calc Chat, 33's at Calc View. Either 43 or 45, they're both at Calc Chat. Do 47 is at Calc Chat. If you want to do that slope field, you can. That's 49. It should be at Calc Chat too. Don't sweat that too much. You'll get that again in differential equations probably. Then do any of the odds 51 to 57. They're all at Calc Chat. 55's at Calc View. Do 59. It's at Calc Chat. Do either 61 or 63 or both. They're at Calc Chat. Either 65 or 67 or both. They're both at Calc Chat, but 67's at Calc View. Either 69 or 71, they're both at Calc Chat. 69's at Calc View. Either 73 or 75, they're both at Calc Chat. 73 is at Calc View. 77 is at Calc Chat. There's an exploring concept there. If you want to try it, you could. That's 79. It should be at Calc Chat. There's a Napier's inequality. Does anyone know who Napier was? John Napier was, I believe, a pastor. So why in the world is he in the math book? Okay? Well, he was also, if you think back to that time frame, actually the pastors were some of the most educated people they had, and because the church basically, certainly during the Dark Ages and Middle Ages, they kept all the education alive. That in Europe, that's the only thing there that was educated. He was a little past that, but he was a very well educated man, but he was also an amateur mathematician and a very good one at that, and he developed logarithms. If it weren't for Napier, I guess we would have developed them. We got them a lot sooner because of him. So you can look at that if you'd like to, or maybe think of that as a paper topic or whatever. And 83 should be at Calc Chat. 85 is a proof. That should be at Calc Chat. You can do any of the odds, 87 to either 87 or 89. They're both at Calc Chat. Population growth is applied problems, as is heat transfer, as is area and slope. So if you want to do any one of those, you could. They should be all at Calc Chat. 97 and 99 are true false, and they should be at Calc Chat as well. Okay. Now, yes?
I have a question. Where did we got 4 over pi, and then we got down 1. Okay, right there we've got log of 2, and when it goes down to the next one, where did the log of 2 go?
Okay. Good question. I was running out of room. This is an answer, okay? In fact, if you look at that right there, that is the answer they give in the book. Log 1 is 0, right? So I was just taking that and splitting that into this and said, or, and this is where I went and did this, and said, where did we get our root 2 over 2? is the same as 1 over root 2. So then this expression here was from root 2 over 2. So this expression would be log of 1 minus log of root 2. Okay? But you have a minus sign in front, so and log of 1 is 0, so that made a minus minus. That I skipped a bunch of steps going from there to here. Okay? And then I made this 2 to the 1/2. That'd be 1/2 the log, and 1/2 the log. Take out that, and that's where you get log 2. I skipped steps like crazy there. I'm running out of room. I wanted to leave the stuff I had there on the board. Sorry. I was just thinking, there's got to be a simpler way to write that answer. There it is. You don't have to go that extremes to get the simplest way to write the answer, but sometimes I get carried away. A lot of times I get carried away. Okay. Now, any other questions? That's a great question. Okay. Let's just go on and scroll through this, and there were the trig functions. Now, I'm not going to do, I hope I'm not going to do very much in 5.3. But let me just show you the PowerPoints anyway. I hope this won't take us too far. The only reason I'm doing any of it is sort of a review, okay? And it also will lead into what we're going to do next. And this is done a little bit differently from any way I've done it or seen it done before. So I'm also trying to help explain why they're, if I can, why they chose to do it this way. Okay. So chapter 5 is logarithmic, exponential, and other transcendental functions. Basically, we've just hit logarithmic functions so far. 5.3 is going to talk about inverse functions. Why that's put in here is because the exponential function is the inverse of log. So that's why I sort of want you to see where they're coming from here. And we're not going to do this in great detail. Verify that one function is the inverse of another function. Determine whether a function has an inverse function, and find the derivative of an inverse function. The first two, hopefully you did. Here comes one of your storms, I think. Yes, that caught up with you, I think. Okay. Okay. The first two, you...
I was trying to get my book to load.
Oh, I see. Yeah, these, the first two are at, you should have done in pre-calculus. You wouldn't have done the third one in pre-calculus. So let's just go through this pretty quickly. A function f of x that maps from A, which is 1, 2, 3, 4, to B, when you do 1 plus 3, you get 4, 2 plus 3, you get 5, 3 plus 3, you get 6, 4 plus 3, you get 7. So that maps into your domain of 4, 5, 6, 7. So there's your function. 1 mapping to 4, 2 mapping to 5. This is the ordered pairs that describe that function. By interchanging the first and second coordinates, you get the inverse function. And that would be, f inverse would be x minus 3. So then if you took your b, subtract 3 from it, you get a for every one of those values. So that would be, you should have had this before, pre-calculus algebra. So I don't want to belabor this any longer than I have to, but that's what you did before. Now that's a very, very simple one. So the domain of f is the range of f inverse, and the range of f inverse is the domain of, the range of f is the domain of f inverse. Okay? So one undoes the other. Okay? Now, when you compose one function with another, f with its inverse, that's the one and almost only time that f of f inverse and f of f inverse of f will ever be the same. In general, if you have two functions, f of g, you do f of g and g of f, they usually are not the same. But when they're inverse functions of each other, they are always the same, and they're always just x. And why? Because the f inverse undid what f was doing. So you started with the f inverse, you start with the x, f undoes the F inverse and it leaves you with X. Or you start with X, you do F on that, F inverse undoes F, and it leaves you with X. You end up with where you started, okay? And this is the mapping illustration of this. You're starting with the X's here, and you take F acting on that, that gives you some new variable, F inverse, and then, F, and then if you do the inverse, you map back here. Or if you start here and go this way, you come back here. So the domain of F is the range of F inverse, and the domain of F inverse is the range of F. So saying the same thing several different times and ways. Okay? So here's the definition of an inverse function. A function g is an inverse function of the function f when f of g of x is equal to x for every x in the domain of g. And not only that way, but g of f of x is also x for every x in the domain of f. Then the function is g is said to be the inverse function of f, read f inverse. Again, this is all stuff from pre-calculus. Here are some important observations about the inverse functions. If g is the inverse of f, then f has to be the inverse of g. Okay? The domain of f inverse is equal to range of f, and range of f inverse is equal to domain of f. We just said all that. And the function need not have an inverse function, but when it does, the inverse function is unique. One and only one. Not all functions have inverse functions, but when they do, it's a unique function. Now, they've done all that, but haven't told you which functions will or cannot and can have inverses. So here, let's go a little bit further. You can think of f inverse as undoing what's done by f. We've said that several different ways. For example, subtraction can be used to undo addition, multiplication be used to undo division, and vice versa. So really easy ones are like this, okay? If f is x plus c, then f inverse is going to be f minus c. If f is cx, then f inverse is going to be x divided by c, okay? As long as c is not 0. So those are inverse functions. Those are really, really, really simple ones, okay? Now, what they want you to do here, and I don't know, I'll ask you, is it worth our time to actually do these? If it is, I'll do them. Do you need to see how to show that they're inverse functions of each other? You take f of g and see if you get x. And you take g of f and see if you get x. If you get x in both cases, they're inverse functions of each other. Do you need to do that? I'll be glad to do it if you want to. What you think? No? Okay. Let's watch how they do it and see. Because the domains and ranges of f and g consist of real numbers, all real numbers. Now, one reason for that is the cube root. If that was a square root, you couldn't say that, okay? But a cube root it is, okay? You can conclude both composite functions exist for all x's, okay? The composition of f with g, the f of g of x, would be 2 times, okay, what you do is plug this g of x, that thing there, in where you see an f and x here. So it would be 2 times that thing there, raised to the third power, and then subtract 1 from it. Okay? Well, when you take a cube root, raise it to the third power, you just get what's on the inside. That gives you 2 times x plus 1 over 2. Well, the 2's will cancel out, and then you've got x plus 1 minus 1, that gives you x. Okay? It's a lot of arm waving, but you see, did those operations, that's exactly what you get. You know, on the way in this morning, they said, there's a chance of rain today. I'd say it's a pretty good chance of rain today. That's all it's been doing in the first 2 classes. It's been raining. Okay. Right now? Okay. A good chance of rain today. So do you see how that gives you x? They'll do all those steps here. The cube of the cube root takes you to there. The 2's cancel out. You get x plus 1 minus 1, that gives you x. Okay? Then you do it the other way, g of f of x, and you put f of x in for g, they lost the g, but g of f of x, g of x was the cube root of x plus 1 over show that here. The cube root of 2x cubed over 2 is the cube root of x cubed, and that's simply x. Okay. So those are composite functions. Those are inverse functions of each other. Because alpha g of x is x and alpha g of f of x is x, you can conclude they're inverse functions of each other. Now, here's another thing about inverse functions. Okay? The graph of them, and here's the thing they haven't told you yet, and I'm just absolutely shocked they haven't. For a function to have an inverse, it must be what they call, does anyone remember? A one-to-one function. What does that mean? It has to be either strictly increasing or strictly decreasing. Okay? And the cubic function, this one right here, here's how it is. X cubed would be basically like that. 2x cubed would be stretched minus 1 down here. So this is 2x cubed minus 1, that's that function. And this function, believe it or not, is this one. Now, the only parts that look like they might be problematic are right in here. That's never perfectly horizontal. It looks like it's close to it, but it's not. You pick an x a little bit on the left side of 0 here, you're going to get a negative number. A little bit on the right side of 0, it's going to be positive. They're going to be tiny numbers, but they are going to always be increasing. And the same thing here. Okay? So that looks like it's almost vertical. It's not quite. It's ever so slightly not vertical. And then you see that these two graphs reflect across the identity function. Y is equal to x. So of course, what do? We exchange x and y. Remember back in that very first example, you exchange your x and your y. So that's how graphs of inverse functions look. So quick review of pre-calc. Okay? They are mirror image of each other. The graph of an inverse is a reflection across the identity function. Okay. All it's saying is the same thing. If f contains the point AB, if and only if f inverse contains the same point, the reverse point, BA. Now, here they finally get to it. The only way a function can have an inverse if it not only passes the vertical line test, which must be a function, but also passes the horizontal line test, this one fails. That is not an inverse function. At the end of the function right here, that would be inverted. If you started it here and went down there, then that would be inverted, because that's either strictly increasing or strictly decreasing, but it can't back up on itself. As soon as it does that, not an inverse function. Okay? So there's the test. Okay? Horizontal line test. So a function has an inverse if and only if it's one-to-one. And that's what we mean. To be a function, for any x, there's only one y. To be an inverse function, that has to be true, but also for any y, there's only one x. That must mean one-to-one. If f is strictly monotonic, meaning strictly increasing or strictly decreasing on its entire domain, then it's a one-to-one function and has an inverse function. Only way it can. Okay. With that graph there, here's a function, f of x equal x cubed plus x minus 1. If you were to plot that, of course, x equals 0 is minus 1, and you plug in these other things, and you see it strictly increasing, that's going to have an inverse. Might be a pain in the neck to find it, but it will have an inverse, because it is the one-to-one function. Passes the vertical line test and the horizontal line test. Okay? And another way to check it, take its derivative, 3x squared plus 1, guess what? Always positive. Never negative, never 0. Always positive. So it has to have, it's strictly increasing. If the first derivative is always positive, that means it's strictly increasing. Okay? Bit better way. You don't have to do a graph. So f is strictly monotonic, must have an inverse function. Finding it might be a pain in the neck, but there it is. Here's another cubic function. This one does not meet past the horizontal line test. Because, see, it backs up on itself and then backs up again. It has two turning points. Its derivative changes time. Now, if you restricted the domain from negative infinity to whatever point that is, it would have an inverse. From this point to that point, it would have an inverse. From this point to positive infinity, that would have an inverse. But this one of this whole domain, not. Okay. Other words, not one-to-one. Okay. Because f of -1, f of 1, and f of 0 are all the same value, so it's not a one-to-one function. Okay, and here's how you go about finding it. Okay, you first see if it has an inverse or not. And actually, the best way to do that is do your first derivative, and then see if it's ever 0 or changes signs. If it does, doesn't have an inverse. Now, if you have y as a function of x, write it out. Okay? Then solve that for x and make it a function of y. Okay? And then that gives you the f inverse of y. Interchange those back again. Okay? Solve that for x, okay, and then that. Then interchange the two variables. What I've always done is interchange the two variables first and solve for y. There, solving for x and then interchange. It doesn't really matter. Resolving an equation for that. Define that as a range of those. So that works, okay. I'm not going to have you doing a bunch of those. I'm just showing you this. This is a review from pre-calc. Okay, so find the inverse of that. First set it equal to y. And then solve for x, and then exchange your variables, or exchange variables and solve for y. It doesn't matter which order you do it, but that's what you'll get. Okay. All right. Okay. So they took a first derivative, showed it's always positive, no matter on the domain. Okay. Now notice the domain here is only from 3/2 to positive infinity, because the square root of this, this thing has to be greater than or equal to 0. So add 3 to both sides, 2x greater than or equal to 3, divided by 2, x greater than or equal to 3/2. The only limit is that part of the domain. Once you do that, then this is always positive as well. So it's strictly increasing. Okay. Then what they do is, set that equal to y, solve for x, you square both sides, and you add 3, then divide by 2. There's your x inverse. Y inverse, okay? F inverse, whatever you want to do. Now they exchange the variables. You can either do it early or do it now, but you have to do it, and that becomes your F inverse. Okay. And then the domain of F inverse, you'll see, is the same as the range of F. Back to this one. The domain here is 3/2 positive infinity. The range here, that's the domain here. The range here is 3/2 positive infinity. The range here is all real values. Your domain here is all real, all positive, not negative. Okay. So you see that works out too. Okay. Okay. You're given, okay, I don't know what they're doing here. Yeah, okay. I didn't do all that, but I showed you on the graph. Okay. You're given a function that is not one-to-one on its domain. By restricting the domain to an interval in which the function is strictly monotonic, you can conclude that the new function is one-to-one. And that's what I've been talking about doing. F of x equals sine x. That is not one-to-one. Okay? It just keeps repeating itself and repeating itself. So there are a bunch of different y values for the same x value. No, wait, a bunch of different x values for the same y value. But if we restrict the domain from minus pi halves to pi halves, that's strictly increasing in that domain, right? So therefore, that is a one-to-one function. Strictly monotonic. Okay? It's clear that it's not one-to-one. Oh, wait, I'm sorry. Unless you restrict it. Sine of 0 is 0 and sine of pi is 0. So if you get outside that, you're repeating yourself. Okay. But it is monotonic, strictly increasing on minus pi halves to pi halves. Because the derivative there is cosine, and cosine is positive in the fourth quadrant and in the first quadrant, which that would be covering. Okay. So there is a picture of the sine function and showing that it's one-to-one on that region from minus pi halves to pi halves. All right. So this is talking about derivative of an inverse function. We talk about continuity, differentiability, that kind of stuff. We really don't have time for all this. But here's something that's sort of interesting. The g prime of x, if f is a function differentiable on the interval, if f has an inverse function g, then g is differentiable at any x for which f prime of g is not equal to 0. And that g prime is 1 over f prime of g of x. Okay? Which is a little bizarre, but it is absolutely true. So, again, this is really where they're going to be springboarding from. And to me, there's a better way to springboard, but you know, this is going to take it formally through it all the way. Okay. This is just using those things. Let's just page on through all this. Okay. Basically, what we're saying here here's your original function, y is equal to f of x. This is your inverse function, y is equal to f prime of x. If at this point here, your slope is 4, then at the inverse point, the exchange point here, your slope is going to be 1. And that basically looks like it has to be that way, and indeed it does. So don't just go by looks. Here, I'm almost certain the slope looks like it is +1 and 1 over +1 is still +1. So those two look like they would be the same. I'm guessing right. But everything else, this is going up sharply, this is going down. It's going up not as sharp. In fact, that is similar. So that's what they're getting at. Okay. And this is a weird way to say it, but is indeed true. If dy dx is the slope of your y is equal to a function of x, but then you do if it has an inverse, x is a function of y, okay, different function, then it's saying that dy dx is 1 over dx over dy, which makes it look, again, like that's a fractional form, because if that was a fractional form, you'd invert multiply, and that's exactly what you would get. So again, what looks like it might be true, but you're dealing with an operator, not a fractional form, is indeed true. You know, it's just like your differentials. It looks like you're multiplying both sides by dx, and basically that apparent thing that you're doing works absolutely really well. Okay, so we won't go into that. Okay. These look like they'd be fun problems, but we really need to move on. Okay. Again, you see that these are inverse functions of each other, and that's a square root function. This is a squaring function. Defined from 0 on. You included this over here? No, not 1 to 1. Okay. But if you just take the right ledge of that, then it works pretty well there. And the slope, yeah, I think we showed that same slope before. Okay. Oh, I guess what they're showing here, because on the squaring function, the derivative here is 0, that derivative is undefined. Okay? Does not exist. So I guess that's what they're showing there. Look like they're showing the same thing as before. All right, that would be the end of that section. You're not responsible for it, any of the problems. But where I'm trying to get to is, and that was one short section for that many slides. That was 1, 2, 3, 4. Well, actually, some of the pages stuck together. So, okay. Here's why we were doing all that, or at least part of the reason. I wanted to get to this function, the exponential function. And we'll both differentiate and integrate. And what we'll do is develop properties of the natural exponential function, differentiate the natural exponential function, which is one of my favorite activities of all times, and we'll integrate the natural exponential function, which is another one of my favorite activities of all time, and you'll see why. Natural exponential function. The function f of x equals log x is increasing on its entire domain, okay? That's anything from not counting 0, but to the right of 0, any positive number, okay? And it's increasing everywhere. It increases quite sharply between 0 and 1. But it's not defined at 0, but from 0 over and 1, it increases very sharply. But from then, it's a very, very, very slow increasing function, but it does always increase. That's what the log function is. Therefore, it has an inverse function, since it's strictly increasing on its entire domain, which does not include 0, by the way, anything to the right of 0, all positive numbers. It has an inverse function. The domain of that is a set of all real numbers, because the range of your log function is a set of all real numbers. So the domain of this inverse function is a set of all real numbers, but its range is of anything greater than 0. Not counting 0, but greater than 0. This is the log function, natural log function. There's your exponential function. We've already named it for you. Okay? Frankly, I like to start with this one and then go do that one. That to me is more fun, but they're doing it this way. That's why I wanted to show it to you. Okay? The inverse of the natural log function is the natural exponential function. Okay? Now, and that's e to the x. Any other exponential function is some number, like 2 to the x, 17 to the x, minus 3 to the x. All those would be legitimate values, I think. Maybe not minus 3. I don't know. Anyway, but the those are the inverse functions of fx equal log x. Okay. And these just lead to some values of that. If x is any rational number in the world, positive or negative, okay, the log of e to the x, remember you can take the exponent and move it out of here, is the x times the log of e, but the log of e, because they're inverse functions of each other, that's 1. Okay? The log of e is 1. So that gives you x. Okay? Because the natural logarithm function is 1 to 1, you can include the inverse of x and e to x. Agreed? Raw. Okay, it's just sort of weasel words there. So the inverse of the natural logarithmic function, f of x equal log x, is called the natural exponential function and is denoted by e to the x. Now you might say, where did the e come from? Have you ever heard of Euler? Famous mathematician, probably shortly after, I think, Archimedes and Newton. You probably have to include Leibniz, maybe, if you're German, you would. But okay, Euler, E-U-L-E-R, was probably one of the next best mathematicians ever, and he came up with the base of the natural number system is E. And I don't know if he named that for himself or someone else did, but that's where the E comes from. So there's a potential paper topic if you want it. Leonard Euler. Okay? So y is equal to e to the x. If and only if x is equal to log y. Those two things, these two statements are equivalent statements. And for one to be true, the other has to be true. That's what if and only if means. The inverse relationship between the natural log, blah, blah, blah. So here's a couple of deals with this. Because they're inverse function, like we just did, log of e to the x is x times log e, which is x times 1, which is this. But also e to the log x, because this is true, that one's also true. And e to the log undoes the log, so you're left with the x. Inverse relationship. Either way, e to the log x is x, log of e to the x is x. And if x, okay. Believe it or not, this is a fairly simple equation. It might look a little hairy, but it's doable. And just for the practice of doing it, let's just do this one. Okay? Solve that equation. How might you solve that? If you see an E, okay. How do you solve an equation? You're trying to isolate the variable, which is x. We want x equals something. That's going to be our answer. That will solve the equation. So we're trying to isolate the x. How do we go about isolating x? If you had x plus 3 is equal to 7, how do you isolate the x? Subtract 3. You do the inverse operation to isolate the x. Same thing here. What's the inverse operation of e? Log. So you do log of both sides. Log 7 is equal to log of e to the x plus 1. Do you buy that? Okay? Well, log 7 is just some number log 7. Okay, we're going to leave that alone. Well, if you do the log of an e, they undo each other, and that's equal to x plus 1. Right? And then how do you solve for x? Subtract 1 from both sides. So x is equal to log 7 minus 1. Okay? Weird number, yes. Guess what, folks? These are irrational numbers. Okay? Just about every ln is an irrational number, and just about every e is an irrational number. Because e itself is an irrational number. It's 2.71 blah, 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 blah. It keeps going forever with never repeating any pattern whatsoever. So that's, log 7 is an irrational number. So your x is going to be an irrational number. So let's see if that's what they got fairly quickly, if I can do anything quickly. Take the natural log of both sides. That gives you log 7 to x plus 1. Subtract 1 from both sides. So that gives you x equal negative 1 plus log 7. I sure like writing it that way a lot better. No, I don't. Okay. But I would have written that as I did write it, log 7 minus 1. Now, the thing you have to realize is don't think that's 7 minus 1 in parentheses. It's log 7 minus 1. That's the one advantage of writing the log at the end. So you don't make that confusion. Okay. All right. So if you want to check that answer, you do 7 is equal to e to the log 7 minus 1 plus 1. Well, minus 1 plus 1, add the 0. So e to the log 7. Well, e to the log is 7. So 7 is equal to 7. So you do this. Is that the same? Just plug in. They do minus 1 plus log 7 plus 1. Well, obviously, plus 1 and minus 1, add the 0. E to log 7. E to the log is just going to be argument 7. So it's a pretty easy thing to do. And it checks. Okay. All right. So, familiar rules for operating irrational exponents is extended to natural logarithmic, natural exponential function is shown here. Anytime you've got the same base, different exponents, multiplying the same base, different exponents, or same exponent, you keep the base, add the exponent. If you're dividing, you keep the base and divide the exponent. If it worked for any other base, it works for the natural base. Okay? Perfectly easy. And A and B can be any real numbers. They say rational exponents. They don't have to be rational. They can be any exponent, any real number. Okay? Now, an inverse function, f inverse, shares many of the properties with f, so the natural exponential function inherits the properties listed below from the natural log function. Because the log, the domain is from, not counting 0, but from all positive numbers, from 0 to positive infinity, not counting 0, that's the range of your exponent of the exponential function, from 0 to positive infinity. Because the domain, the range of the natural log function is from negative infinity to positive infinity, that becomes the domain of e to the x. Okay? Function e to the x is continuous because the log x from x greater than 0 is continuous. So 1 to 1, 1 to 1. It's increasing, they're increasing. Okay? They're both. Okay? Now, here's a little different. Log function is concave down, exponential function is concave up. But it's got to be because they're inverse of each other. Okay? They reflect across the identity function. Okay? Now, the limit as e to x, as x goes to minus infinity, the limit is 0. It never reaches there, but that's going to be its limit. And the limit as x goes to positive infinity is definitely going to be positive infinity. It's going up incredibly rapidly. You don't have to get very far at all on the x-axis before your e to the x is out of sight. So it's going to positive infinity. Now, derivatives of exponential functions. This is my favorite. That's why it's my favorite function of all time. One of the most intriguing and useful characteristics of the natural exponential function is it is its own derivative. The derivative of e to the x is e to the x. Period. Okay? Now, if you had a function up here, e to the u, derivative of e to the u, would be e to the u, but then do the chain rule, du dx. So that's going to come in so incredibly handy later. Okay? So let's do this one. What would be d by dx, I like saying that, of e to the 2x plus minus 1? What do you think it would be? Anybody? Help me. E to the 2x minus 1, because it's its own derivative, but then you do the chain rule and do the derivative of the inside, which is 2. No, just 2. Derivative of that. Derivative of 2x minus 1 is just 2. There it is. Love taking derivatives of exponential functions. They're the function itself, and then if you have a chain rule, then do the chain rule on it. Does that make sense? Okay. Derivative of this thing is that thing. Okay. Then times the derivative of whatever the chain rule is. Derivative of that is merely 2. I like the 2 on this side. Just make it easier to see. Okay? And let's see how they did it. Whoa, they did it right on top of them. I wrote mine up there so it wouldn't interfere. They said e to the u du, or the u was 2x minus 1, so it'd be e to the 2x minus 1 times du. d of 2x minus 1 is just 2. Put the 2 on the other side. All right, how about this one? What would this be? Any ideas? At least get me started. E to the minus 3 over x. Okay, that's the e to the u. Derivative of that is e to the u. Okay, but now we got to do the derivative of this, the chain rule of that. So what is d by dx of minus 3 over x? Well, I don't like taking derivative of things in denominators, so I'm going to rewrite it an exponential thing, e to d by dx of minus 3, yuck, getting exponentials on the brain here, okay, x to the minus 1. That's a lot easier to do, isn't it? What is that derivative? Help me. Anybody? Second. 3. X and minus 2. Got it. So that would be 3 over x squared. I don't know if that's how they're going to write it, but that certainly is one way to write it. Does everybody see that? Taking the derivative of exponential, write down the exponential. It's always going to be there. Then take the derivative of the inside, and that's what I went over there and did. And I like to write it in exponential notation rather than fractional notation. And when you did that, the derivative of that is 3 over x squared. Okay? Want to see how they did it? Hopefully it won't be a lot different. It'll be e to the u du. E to the u is e to the minus 3 over x times 3 over x squared. They didn't show how they did that derivative, but that's what they get. Same thing that we got, right? Any questions on it so far? Yay or nay? Okay. Oops. And they would have to turn around and write it some other way. I see no advantage of this over the previous one whatsoever. But it's absolutely correct. Do the 3 with the e to the minus 3 over x squared. I see no reason to do it, but they did. Both of them are fine. How about this? d by dx of x squared e to the x. What is this going to entail?
X squared times e to the x.
Which means that's a product rule. Because you said times, right? So let's do the product rule. What would that be?
It's the first times the derivative of the second.
Okay, so that'd be x squared e to the x plus
the derivative, the second times the derivative of the first.
Yeah, which would be
well, it'd be 2x times
e to the x. And then, if you wanted to, you could factor out an x e to the x, and you're left with x plus 2. X plus 2. I can say x plus 2 and write down 1 plus 2. Okay. Now, I don't know if that's how they're going to write it. That, to me, is the simplest way to write it. This is the first times the derivative of the second, plus the second, which is e to the x, times the derivative of the first, which is 2x. And then notice the factor of x, e to the x, in both of those. Factor that out, and that leaves you x plus 2. Let's see if that's how they do it. Again, there's many ways you can write it, and there's nothing wrong if you're doing it in whatever web assigned. They only look for one correct answer where there could be many. Yeah, and they left it the same way. Okay? Make sense? Yay or nay? Any questions? Okay. I think there may be a D here. Ugh. They're getting worse and worse, aren't they? Okay? Now, normally, if there's any way around it, I will change a quotient rule to a product rule, and you could do that. However, I don't think it's going to make things a lot better, so let's just use the quotient rule. What would that be? What will that be? Anyone remember the quotient rule?
D low.
Okay, it's low D high. Yeah, no, start with low. Low D high, which is e to the x plus 1, that's the denominator, that's what makes it low, times derivative of the numerator, which is
E
3 e to the 3x, right? That's, boy, my writing stinks. I'm not sure you can read my writing. Let me. Goodness gracious. Okay. All right. The low D high part is the denominator, the low part, times the derivative of the numerator, which would be 3 times e to the 3x. Right? You buy that? E to the 3x times the derivative of that. Okay. Minus high D low, which is e to the 3x, and what's the derivative of the denominator? What's the derivative of the denominator? This is the D low part. Somebody help me. Derivative e to the x dx. Wait a minute. Okay. Aren't we supposed to be through at 11:15? No. Wait. 11:40. Good. Whew, I thought we had gone over. Okay. What's the derivative of the denominator? E to the x. That's it. Okay. Because the derivative of 1 is 0. And what's that all over? Denominator squared. It would be e to the x plus 1 squared. Now, how could we write that? I'm not saying we should, but if we wanted to, that would be e to the 2x plus 2e to the x plus 1. But I see no advantage of that. In other words, you square the first, which is e to the 2x, plus twice the product, plus 2e to the x, plus whatever that. But again, I see no advantage of doing that, so even though I did it, I just did it to show it to you. I didn't think of any way that's improving. Now, let's see if we can monkey some with the numerator and get it to say anything better. Well, this is a monomial times a binomial, so let's multiply them through. That would give you 3e to the 4x, right? Plus 3e to the 3x minus e to the 4x over, I'm just going to leave this as e to the x plus 1 squared. Okay? Well, this just gives you 2e to the 4x. I can't write, goodness gracious, plus 3e to the 3x divided by e to the x plus 1 squared. I can't think of any simpler way to write it than that. I mean, yeah, you can factor out e to the 3x and leave your numerator to be 2e to the x plus 3. Yeah, I don't see that as any better, but you could do it. E to the x times 2e, no, I'm sorry, e to the 3x, factor out 3x, 2e to the x plus 3 over e to the x plus 1 squared. I don't know that's any simpler, but you could do that. Let's see what they do. Hopefully I haven't done some really stupid error. Okay, denominator times the root of the numerator we got, minus the numerator times the root of the denominator we got, over that thing squared. See, they didn't square it out. And then they did that step, which we did, which is, yeah, they did factor it out. E to the 3x times 2e to the x plus 3 over e to the x plus 1 squared. I can't think of any simpler way to do that. So, done. Let's see where we are now. Okay. So let me go back. I skipped example 2. They skipped it, and I skipped it too. Let me go back to example 2. Sorry about that. Okay. Example 2. Solve this. Log of 2x minus 3 is equal to 5. I say solve that. I want to find out what x has to be. How do we do that?
Start by adding 3.
That's inside the argument. Not yet.
Oh, yeah.
Okay. You want to what?
Try to get rid of the ln.
Get rid of the ln. Undo the ln. How do we do that? What function? Second? E. So e to the ln of 2x minus 3 is equal to e to the 5. You got to do it to both sides. Got to be democratic about it, right? Okay. Now, what does the left-hand side give you? Help me, help me. The e undoes the log, right? So you're left with 2x minus 3. And that's equal to e to the 5th. That's just a number, by the way. Okay? And then what do we do? Want to solve for x. Say again? Add 3 to both sides. So that gives me 2x is equal to, that's That's an equal sign. I think, what in the world is that equal to? Okay, equal to, I'm going to put, like they did before, 3 plus e to the 5th. Otherwise, you put the 3 on the other side. You don't know if it's 5 plus 3. It depends on how sloppy your writing is. Okay, which mine is pretty sloppy, by the way. Okay. And then the last step is divide by 2. So your x is equal to 3 plus e to the 5th divided by 2. And they put 1/2 e to the 5th plus 3, which is fine. Any way you want to do it gives you the same. Okay. Just wanted you to see that because we did the exponential equation. This is the log equation. That's how you solve it. Okay. I'm trying to figure out where I left off. We did that, we did that, we did that, we did that, we did that. Say again? Okay. Okay, we did example 3. Now, they skipped 4, 5, and 6 and go to integrals of exponential functions. What do y'all think? Locating relative extrema, do you think you can do that all right, or do you need to do that? In other words, find the relative minimum or maximum of x e to the x. You kept okay with that, or do you think we need to do it?
Is that where you find the second derivative?
Only first. If you all you're looking for is max or min, just find the first derivative, set it equal to 0. If you're looking for concavity, do the second derivative. Y'all need to do it or not? I'll be glad to if you want to. Tell me. Do it or not? Huh? No. We're not doing concavity now. We could do it if you want to, but all they're looking for is locating the relative minimum or maximum. Want to do it? Good with it? Yeah. Okay. Everybody's okay with it?
That's like one of the last things we went over.
What's that?
Last semester, that was like one of the last things we went over.
Right. Okay. Then example 5 is finding the equation of a tangent line. Remember how to do that? You want to do that? Basically find your first derivative at the point that you're interested in, then plugging in. You want to do it or not? Yay or nay? Do that? Okay, did you want to do the previous one?
That's better.
Huh?
We only have 5 minutes left.
Okay. Oh, I talked my way out of it. Okay. Let's go back and do, well, we can do one or the other. You want to do example 4 or example 5?
Let's start with 4.
4. Okay, let's do example 4. So here's a function. F of x is equal to x e to, I'm sorry. I was thinking the other way. X e to the x. And we want to find relative extrema. So what do we do first? Take a derivative. F prime of x is equal to what?
EX.
It's what?
EX.
E to the x will be one of them. Anything else?
The X is just 1.
Second?
I mean, the X is just 1, isn't it?
Okay, the derivative of x is 1. Okay, but this is a product rule. It's x times e to the x. You still go with that first one?
No.
You don't, okay. So what would that be? Anybody? What would be the derivative of that product rule? How does the product rule go? Say again? Say again?
We would say something, or I think it would have been like EX minus 1. That's what I'm thinking, because it's taking a derivative, but it doesn't sound right.
Okay. If that was an n, then you subtract a 1 from it, but it's not an n. That's not a number, it's a variable. So, but how does the product rule go?
So it'd just be EX plus X.
Okay. Okay. Close but not. Okay. How does the product rule go? First times derivative of the second plus second times derivative of the first. Or whichever order you want to. So which you want to do first? I don't care. Huh? First. Okay. The first is just x times derivative of e to the x is e to the x plus the second, which is e to the x times derivative of the first, which is 1. So there's your first derivative. Okay, and what do we do with it? To find the local minimum or maximum, set it equal to 0. Okay? Now, here we can factor, can't we? Factor out e to the x, and you're left with an x plus 1. Now, is that what someone was saying earlier? It sounded like you were getting awfully close to saying that, but I couldn't quite make it out. Had you gone that far to separating them like that?
No.
Okay, no.
I was doing it like a derivative. You was trying to put me on the right path, because you're saying it wasn't a number, it was a variable. It was a variable. So
Right. Yeah. Yeah, if it was a number, you would do subtract 1. With a variable, the derivative of e to the x is e to the x. Okay. All right. Now, what do we do with that? You have factor a product of two entities is equal to 0. What does that tell us? Either
One of them has to be equal to 0.
one of them's not going to be equal to 0. So either e to the x is equal to 0 or x plus 1 is equal to 0. Okay? When is e to the x equal to 0? No, x equals 0, e to the x would be 1. E to the 0 is 1. E to anything is 1. Or anything to the 0th power is 1. So, I don't know the other one you said.
That's why x equals 1.
E to the, if x equal 1, e to the 1 would be 2.7 blah, 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 blah. You know, it's an irrational number, but it's that number. So that's not equal to 0. When is e to the x equal to 0? What's that? When is e to the x equals 0? Okay, draw me a picture. At x equals 0 is 1. And then from there on, it's going up like this. And from here,
So
it's never equal to 0. Okay. That's why thinking in terms of the graph sometimes helps. Okay. So this one is never equal to 0. So what is the only other option? X equal -1. And then you plug that in and see what the y value is. So the y is equal to, or alpha of -1 is equal to -1 e to the -1, which would be -1 over e, which is something about -1/3 or something like that. Okay, and sure enough, there it is. It's at -1 is the x value, -1 over e is the y value. That is the point, which is a relative extrema, and you haven't figured out which one it is, but which one you reckon it is. Minimum or maximum? I'll show you the graph, but when x is negative, this is a negative number, but this is getting closer and closer to 0. That's negative. So it's a negative number, but it's getting closer and closer to 0. Okay? You have a relative not to be a minimum. Okay. Now, we'll begin next time at example 5. I'm trying to do these sort of quickly, but I want you to make sure I'm not skipping anything that leaves you blank, something you need. Okay, so we'll pick up at example 5. On these, try to do some of these homework exercises, any of the odds 3 through 17. They're all at calcchat.com, 9's at calcview. You might find 19 through 23 somewhat useful or not. But try sketching some of those. And then 25 to 28 would be good to do all those. You only find answers for 25 and 27 at CalcChat, but try to do them all, okay? And then do any of the, either 29 or 31, they're both at CalcChat, 29's at CalcView. Any of the odds 33 to 53, they're all at CalcChat, 33's at CalcView. And we didn't get to find the equation of a tangent line. We'll do that next time. So stop at 53. Good deal. All right. We'll try to move quickly through this because I want to get on to maybe just a slideshow of 5.5. But we do need to do a little bit in 5.6. Okay, because we'll run into that later. And I don't think we'll need to do anything in 5.7. This is one long chapter. And 5.8. I may just show you the slides on those. Those are all. And we're not going to do anything in 5.9. So I think this is going to be awfully close to finishing up. So if we can finish this section here, which is 5.5, no, 5.4. And I think the rest will just be slideshow stuff. I think. We'll see. I believe so. I'll try to have your first test ready for you there. I almost got it ready for you with chapter 4, what we did in that. But I said, no, I think we really need to include 5 in that. So we'll do that. So hopefully have that ready for you, maybe Monday. You don't have to take it then if you don't want to. I'll try to have it ready. Okay, good deal. Sorry I went over a little bit. But the good news is no extra charge. Okay. Any questions? A lot of silence at the end. So.